Yep.
This last one.
Yep.
I guess I'm gonna say it's right by Thanks.
Well, what would it have to be for it to have a critical angle?
I'm just guessing. Well, it have to.
There's only one possibility. You can't get a critical angle going both ways. There's only one way that will get a critical angle.
Yeah. Well, I know what it is. I was just asking if it's around by
I mean,
That's what it says. Well, it's just when it's around by air, I just don't know if it's.
that's just saying air is the other medium, not me.
Obviously, Audrey.
Okay.
I don't. Holy cow.
Okay. Did I start that? I think I started that. What's the matter?
Audrey just has last beat. We're gonna give us 10 with like 4 digits. Are we graduating? How to make sense? Equals 4 digits.
I mean, have I talked to different things all year?
No, but.
Okay, I don't have any homework that I need to come check. However, I think there are a few of you that might have something for me. I think there was one other.
Did they turn on?
Yeah. Who was the other person? Moira, did you get that done? The one that you didn't do yesterday? You told me yesterday specifically that you told me you didn't get done and why you didn't get done, and I don't remember it. Okay.
You go back.
All right. Where do we? What? We did acoustic.
Well, we wrote it down. You didn't really talk about it.
Oh, okay, so you want me to talk about it? Is that what you're saying?
Yeah.
Oh, a turkey! Gobble gobble! There it is. Thank you, turkey. Hey ladies, you guys need to be getting done real soon here.
Okay.
I said 5 minutes. Avery? Yeah, acoustic energy. We said acoustic energy is equivalent to what kind of energy? Sound. We're talking about sound here. Okay? Acoustic energy is the result of vibrations of matter. Makes sense? What's vibrating when you talk? Your vocal cords. Yeah. Have you ever seen slow-mo of someone doing this?
Maybe we should watch a video of it, yeah.
It's pretty, I mean, you can see spit flying and everything too, but yeah, it's definitely a vibration. Okay? So sound always starts with a what? Vibration. Okay? That vibration, okay, that starting vibration causes matter to displace as energy travels through it. Here's the kicker for sound. It cannot move without matter. Okay? It always moves through matter. So what if we had a vacuum? Could you hear sound? No. So if I put your cell phone in a vacuum and called it, you wouldn't be able to hear it. And assuming it was a perfect vacuum. Like, well, how did the astronauts, somebody asked me this, how did the astronauts communicate with each other? Well, first off, they're in the space shuttle, which better have air. Why? Because without air, they would what? Die. Okay? But yeah, then if they're like out of the space shuttle and they're in little space suits, yeah, they'd have to use some sort of device to communicate. Because it's not going to go through outer space. Sound will not travel through outer space because outer space is virtually a what? Vacuum. So it's got to have matter for the vibration to displace it. Okay? So I'll say about that. Let's move on. Electrical.
sorry.
4?
You're a disappointment, Cheyenne, after you grade that test.
I'm sure it'll be just like it always is. You done?
No, I'm not finished.
Okay, so the first form of energy we talked about yesterday was thermal. Second form was acoustic. Our third is electrical. Now, this is kind of one of those forms of energy that you could take one chapter, probably 2, talking about. It's a big portion of physics. Okay? Now, we're not at a level where we're going to spend a ton of time talking about electrical energy, so I'm just going to give you the big picture here. First of all, electrical energy creates a force, and what kind of force is it? From last chapter, a field force. Okay? So what charged particles do is they create an electrical field. If you move into that electrical field, you feel a force. A force at a distance. Okay? Now this is probably something that you may or may not know, but probably didn't know. Okay, we use electricity all the time, correct? Okay, so when you plug in something into an outlet, let's say, a lamp. Okay? What electricity most often is moving electrons. You guys know that? Yeah, no, maybe so. Okay? Now, it's very complicated. It's not just simply, saying, oh, electrons move through and push things. No, that's not. It's more difficult than that. But in its basic form, really what you have for electrical energy is a result of moving electrons. Okay, from a high dense place of electrons to a lower. What do electrons do to each other? Attract or repel? They repel. And so if you can get a bunch of electrons to be stored up in a location where they repel each other, they have a lot of potential to flow. Okay? And that's why after all the electrons have flowed from the buildup to the not built up, your batteries and things like that, eventually they what? Your batteries eventually die, right? Okay, there's only so much electrons that you can store up in a battery. Okay, well, why does light bulbs that are connected to outlets not die? There's a constant flow of electricity, electrons from a power plant that's generating all these electrons. Does that make sense? Okay. Right. Magnetic, another form we're going to just kind of get a big picture of. Again, it could take a whole chapter or 2 just talking about magnetic. You probably are familiar with magnets. Have you ever heard of the North Pole and the South Pole of a magnet? Usually when you hear of North Pole and South Pole, it's like Santa Claus. Right? No, not really. No? So you're saying you're more familiar with magnets having a north and south pole than Santa Claus's North Pole? I'm shocked. I thought that was like, what? What? You said something.
He said something, but he doesn't want to.
I ain't gonna do that. Did you know there's a North Pole on Earth and a South Pole on Earth? This is probably what you didn't know. The Earth is a magnet. The North Pole is the magnetic pole of the Earth, and the South Pole is the opposite magnetic pole. Now I don't know off the top of my head which is the positive, which is the negative. I don't know that off the top of my head. But when they say the North Pole and the South Pole of the Earth, they're referring to the magnetic charge, the magnetic components of the Earth. Now, they're very closely related to electricity. Magnets are. They deal with electrons as well. I think that's about all I'm going to say about that. Questions that you've always been wanting to ask about magnetic or electric things? Yeah? What?
Yeah, there's definitely.
Thanks. Got it? Yeah? Do they work together? Yes. In fact, we'll talk about electromagnetic energy soon, and that's light. Is a, well, we'll get to it when we get to it. Yeah, I'll explain it when we get there. Oops. Another word for radiant energy is electromagnetic energy. Yep. So you get this and then I'll talk to you about it. So radiant energy is what energy? Don't say electromagnetic. What's the other word that I could probably put in there? Light. Maybe I'll do that, just so you're aware of that. Radiant is also known as light energy. Okay? So, what's unique about light energy is that it doesn't need a medium to travel through like we said sound does. And thankfully, it can go through a vacuum, because if it couldn't go through a vacuum, would we have light on Earth? No, because where do we get our light source from? The sun. Okay? So if the sun couldn't transmit light through outer space to the Earth, we wouldn't be able to see it. Okay? So Electromagnetic light isn't the result of vibrations. What it is, it's very complex, is it's an electric field that produces a magnetic field, that produces an electric field, that produces a magnetic field. So basically it's an oscillation of electric and magnetic fields that cause it to propel through space. And that doesn't mean a whole lot to you at this point, I understand that. It's pretty complex. Okay, here's something that you probably didn't know. Radio waves, light. Microwaves, light. X-rays, light. Gamma rays, light. UV rays, light. Infrared rays, light. Yes?
So in a microwave, when you put the food in, when you close the door, the light comes on.
That's not that. That's actual light inside the microwave. When I say all those are light, that doesn't mean we can see them all. Stop it! The only light that we can see is visible light. And even visible light has various different light colors. Like when the sun comes through a prism, has anybody seen white light shine through a prism? It looks like a rainbow. That's because what it's doing is it's refracting the white light into all of its different wavelengths, and so you can see all the different visible colors of light. The reason why his shirt is black is because white light comes in, hits his shirt, and it all absorbs, so no light reflects to our eyes, and it looks like no light coming, and that's what black is. When light comes in, hits Matea's shirt, all of the colors, not, what is that, peach? Salmon? Okay? All the colors not salmon or peach get absorbed, and only the salmon-peach combination is what we see. Yes?
Does that mean that black is not color, just black color?
Yeah. Black is not a... When you see black, you're not seeing light. When you see white, you're seeing all of the wavelengths of light combined. So when light comes in and hits Rose's shirt, none of it's getting absorbed, and it's all getting reflected back to my eye, so I see white light. When the light comes in and hits Steven's shirt, green shirt, all of the wavelengths of light get absorbed except for the green wavelength. It gets reflected back to our eye, and that's why we see green. Mind blown, right? Here's a... Steven's colorblind? I forgot. Did you know that was green? Okay. Did you know I was colorblind?
You're
colorblind?
You didn't know that?
He's not, guys.
That makes no sense, guys. I just said his shirt's green. How would I? You guys are so gullible.
Wow.
You guys are so gullible. I know. I once got a class because I was colorblind for like
it was not
weeks.
his class.
Yeah, Mr.
Yeah.
Mr. French's here.
This is
Last
for the
thing that he
teacher
was
that was
talking
only
about.
yellow colors. Yeah,
Speaking what? So, light is pretty cool. The only thing that probably was overly crazy that you may have not have known is that there are multiple forms of light, but there's only a small fraction of it that we can actually see. Remember how we talked about potential energy earlier this week and Friday last week? It's in the definition of chemical energy.
So it's sort of in the compounds of
In the chemical bonds that are in the compounds. So like there, this is a compound. The energy of bonds. Okay, I think I've talked about breaking bonds requires energy, forming bond releases energy. Have I talked about that or no? No, don't remember. Okay, I will talk about this then as well. I'm going to take a little bit of time and camp on this a little bit because it is a pretty big important part of chemistry. We'll get much more into this if it's in chemistry. But here we go. Breaking bonds requires energy. That usually makes sense. If you break things, you're probably going to have to put an input of energy, right? That usually makes conceptual sense to us. What doesn't always make conceptual sense is the idea that forming bonds releases energy or gives off energy. Okay? Let me explain this. Do you remember last semester we talked about the chemistry side? Shane said, "You're all right." I know, it's rough. It's been a long week, it's been a long year, it's been a long life. Anyways, where was I? Oh, well, we talked in chemistry last semester. We said things bond, right? Remember talking about how things bond? Do you remember why they bond? To become stable. And what did we say stable meant? That's how it becomes stable. But what does stable mean? Low energy.
Low energy.
You guys don't remember that?
Yeah, I do.
Low energy. So, things bond to have low energy, which means that they had high energy before, right? So when they bond, they form bonds, correct? So they go from high energy to low energy when they form those bonds. Well, where do you think the energy goes?
Out.
Out. Releases. Okay? So when bonds form, they form to lower the energy from high to low to become more stable, and in the process, energy leaves. That's why the formation of bonds releases energy. Okay? And the breaking of bonds requires energy. Because if I am stable bonded, if I'm going to break those bonds, I'm going to have to put energy in because it's more stable, more unstable after I've broken the bonds, right? If I have H2O, it'd just be opposite, guys. Stable, right? Yeah. If I have oxygen and hydrogen by itself, we said that is not stable, correct? Okay? Low or high energy? Low energy? How about this? High energy. Wow. Why did I do it that way?
Kremlin.
Why? I did an energy, H energy versus, oh my goodness. So, if I go the opposite, if I'm going to break water into its atoms, which aren't as stable, I'm going to be going from low energy to high energy. So what had to have happened? Energy had to have come in, right? The opposite, right? If I form to make it stable, energy being released. When I break to become non-stable, energy is absorbed to get high energy unstable things. Okay, got it. Got it. Nuclear! Boom! I almost gave the turkey a bath with hand sanitizer. A hand sanitizer bath. What? Yeah, it does. Can I have some hand sanitizer, turkey? Sure. Thanks.
Wow.
Don't mind them. They're silly.
Take it away. You're gonna be weird.
Are you an Indian giver?
What?
Yes.
What did you say?
You gonna take your gift back?
You're gonna use it correctly.
Yeah, use it correctly.
Don't confiscate it.
Remember, why aren't you playing in 2K?
What?
Why aren't you playing in 2K?
Why didn't it? Because no one had the stuff.
I was literally playing Dino. Could have played against me.
I don't want to hurt your feelings.
I would have destroyed you.
Okay. Nuclear energy. Where do you think the energy is when we talk about nuclear energy? Tired there, Moira? Me too. I've had a long life.
It's only been 2.
You're a culprit.
I know. I'm not going home between now and conferences. I'm gonna be here from 7 in the morning till 8 o'clock at night. Put in a 13-hour day, ladies and
You
gentlemen.
like conference?
Do I like conferences?
I can't wait till spring break.
Okay. So, where do you think nuclear energy is found? In the nucleus. Guys, the energy stored up in the nucleus is the most powerful, highest amount of energy we've ever seen or experienced.
Is that why there's nuclear bombs?
Yes. Yep, when you do nuclear bombs, that's why they're devastating.
Yes.
Okay, that should make sense. Okay, have you ever thought, what is in the nucleus? What's in the nucleus, guys? Lots of protons and neutrons. What are the charge of the protons? What are the charge of the neutrons? Okay, who said negative?
They don't have a choice.
He did.
You definitely said that.
Mari!
What?
You're dead to me.
Thank you.
You're dead to me.
You can't say that.
What did I say?
You said negative.
They don't have a choice.
Watch them.
Alright, protons are positive, neutrons are
Negative.
neutral. You're influencing her now.
You're welcome.
They're neutral. Okay, what do positive things do to other positive things?
They
Repel. So
Repel.
what in the world could potentially even keep the positive things from repelling? Maybe a whole bunch of nuclear energy holding it in.
Wow.
Come here. Fission, fusion. Okay, they're very similar words, aren't they? What, 1 letter difference?
No, 2 letter difference.
Yeah, okay, 2 letter difference. Okay, they're opposites of each other. Fission is when the large nucleus splits. Fusion is when you've got a nucleus that gets combined. So it's energy going in versus energy coming out. What's the matter? You got a little hole in my pants?
No. I made a joke. It's not me. It's not about you.
What happened?
Last form of energy here. Mass energy. Do you guys know mass has energy? Energy has mass. That's where that infamous Einstein equation works. It's not about me.
I think it is.
It's not. It's not.
Who's it about? Is it about a student?
No.
Is it about a teacher?
Previous teacher.
Previous teacher.
You should. It's probably about Miss Stover.
No. No. Although it would probably work for that too. Correct. No.
Yeah, let's not do it. That's called gossiping.
Okay, so tell us. That's
One
called
of the
gossip.
respectable sins.
Wait, are you talking about telling us would be gossip?
I know our sin nature wants to hear it. Because you want to know why we like gossip so much? Because it makes us feel better.
Yeah, that's true.
This last one.
That means I have no homework. I did my homework yesterday.
Good job. Good job.
I did go in.
Okay. What?
So irresponsible.
Yes, the homework I gave you yesterday is due tomorrow. Okay. Hold. I do want to explain this here. I didn't turn this on, right? I keep wondering. Okay. First bullet up there says this is the largest potential source of energy in the universe. Why is that? Because, yeah, we got a lot of mass. And you can even say that the sun, what that is that mass energy is converted to nuclear energy, is converted to light energy, is converted to heat energy, and so forth. Okay? So the sun is made up of a very large massive object that has a lot of energy. This has been blowing people's minds for centuries, that energy has mass and mass has energy. I can't even wrap my mind around this that much. Why? Because it's not that hard to know that mass can give us energy, but it's really hard for us to understand that energy has a mass. Like light, as it's traveling through the air, is energy, right? Can you weigh light? No. But it has mass. Right. But it doesn't have mass from the traditional sense. It has mass from an apparent sense, which is really, really complicated. Now, I just gave you a bunch of different kinds of energy sources. Now, you're probably wondering, I thought you said there was 9. Well, yes, but let's name some of them. Radiant. Thermal. Mass. Magnetic. Electric. Acoustic. Did we say nuclear? I think we did. Chemical. And there are 2 more that weren't part of this lesson. Potential. Kinetic. All right, you're done.
Yay.